As the name suggests, combustion analysis is a way of looking at the composition of a particular chemical by combusting it and then looking at the resulting products. So this machine that you all see right here is a combustion analyzer. It's a Perkin-Elmer 2400 Series 2 analyzer, to be specific. So you can tell it looks for C, H, N, or S. The thing costs about 100 grand. One of the many reasons we don't own one. This is sort of what happens inside a combustion analysis machine. So you can see initially over here, you have your sample in that little box, and you bring excess oxygen in order to completely combust it inside the furnace. This is important. There's a lot of oxygen, and the sample could contain carbon, hydrogen, and oxygen. It could contain carbon, hydrogen, and some other thing, like chlorine, sulfur, nitrogen, whatever. For right now, let's just pretend it's carbon, hydrogen, and oxygen to make it simpler. So the next sort of trap or piece of the machine is basically a copper 2 oxide catalyst. What this does is make sure that all of the carbon is converted to CO2, all of the hydrogen is converted to H2O. So in other words, if we had this initial substance, we're combusting it in oxygen, it's going to make CO2 and H2O, and we're ensuring in this container right here that this reaction is happening completely, so that there's no leftover stuff here at the end of the reaction. In this next part that you can see, in this next part you can see here, this water trap is a place where basically all of the water binds to magnesium perchlorate, and therefore you can find the mass of this thing initially and at the end and subtract in order to find out how much water there was in the product of this reaction. Similarly, you can do the same sort of thing over here with the CO2 trap. NaOH combines with the CO2 to make sodium bicarbonate, which is NaHCO3. This part's not really important, except to know that you can figure out, again, how much CO2 there is in the actual sample. So the point of all this mess is that you can figure out exactly how much water was produced in the chemical reaction and how much CO2 there was in the chemical reaction. Here's what an actual problem looks like. Take a second to read through this. Actually, just pause the video. Okay, so now that you've read through the problem, you can see we start off with this much of the compound, and we're producing this much CO2 and this much water. All right? So our first task is to find out the empirical formula for this thing. So unlike percent composition problems, we don't want to immediately start by looking at percent composition. Instead, what we're going to do that's sort of like percent composition problems is we're going to be looking and we're going to see how many moles of carbon there is compared to how many moles of hydrogen there is. Okay, so I'm going to give you all sort of the skeletal outline for how to do this sort of problem. So again, these are combustion analysis problems. Okay, so what we're going to do is start with the CO2. So we start with milligrams of CO2, and we're going to need to first just convert that to grams of CO2. Then, in order to compare moles of carbon to moles of hydrogen, we're going to turn that into moles of CO2, and then into moles of carbon. This step is pretty easy. All you need to do is look, there's a 1-to-1 ratio between the carbon and the carbon dioxide that's present here. So for every 1 mole of carbon dioxide, there's 1 mole of carbon. Okay, so similarly, we can do milligrams of H2O, grams of water, to moles of water, and then to moles of hydrogen. This one's just slightly more complicated. 2-to-1, right? 2 moles of hydrogen for every 1 mole, 2 moles of hydrogen for every 1 mole of H2O. All right. Hope you all are good thus far. Remember, you can pause this thing if you are confused or go back, listen to it again. For the oxygen, it's more complex. You might think that we could just figure out how many moles of oxygen there were here and do that same ratio thing, moles of oxygen here, add them together. But remember excess oxygen. So if our sample started off as C, H, and O, some of the oxygen that's present over here came from the actual sample. Some of the oxygen came from the oxygen gas. There's two places the oxygen came from. So we have to be more tricky. What we can do is the following. We can basically take the moles of carbon, the moles of hydrogen, turn them into grams, and then subtract that mass from the original mass up here. Because if the sample only contains carbon, hydrogen, and oxygen, like it says right here, then if we subtract this gram and this gram from the original mass, we'll be left with just the mass of oxygen. So, in other words, convert moles of carbon to grams of carbon, moles of hydrogen to grams of hydrogen, subtract the following. We take the total mass of the compound minus the mass of the carbon and hydrogen, and that is going to give us the mass of the oxygen. Then from there, I guess this is sort of step 3, turn mass of oxygen into moles of oxygen. And now look, now we know, moles of oxygen. Now we know the moles of oxygen, the moles of hydrogen, the moles of carbon, and we can do that same thing we did with the percent composition. We can say divide all these things by the smallest one in order to get the ratio, and then multiply it until we get the whole numbers. So that's combustion analysis in a nutshell. Here's one more place you can look if you need, or actually here's one thing you should look at next. You should look at the handout that I either gave you or am going to give you that is a sample combustion analysis problem. This one's really obnoxious because there's all this annoying number math in it, but take a look through this, and this is everything I just told you, but in much more annoying detail.